We have now 90 minutes to play around with this and see where we got. Already, just by playing it, got some interesting results that I don't even fully understand what they mean. So it might be interesting. And as always, anytime, jump in, ask a question, make a comment. At some point, I will ask you what we should be doing because we have to decide what we want to do. So we discussed earlier that the ones we want to use is a simulate virus and ER ODE, which corresponds to this app here, this model, the underlying one. So I went ahead and for here just opened it. So that's the basic, that's you get when you hit the download button, you get that zip file with all the R code in it. And so you get this one here. So all this stuff, we've not really talked about it much, but this thing at the top of these scripts is really just for when you ask the help file for this function, it will tell you how to use it. And also this is displayed on the graphical interface. So if you write R functions for general consumption for the public, then you need this. If you just write things for yourself, then you don't actually need all this stuff here. And the real code really only starts here with this one. So what I did first is I made a copy of that to not confuse myself or anyone else. I renamed it to _new instead of _ODE. So we just keep them straight. So this is now our version of this function. So what I did, first I deleted all that stuff at the top and just wrote some quick comments in there. So, for this purpose here, we don't really need all this. It's always good to have maybe some explanation somewhere that, tells you or the user what these different parameters mean. You should write it down somewhere. But I figured for now, it's just, maybe in the way. We can always look back here at the app and the explanation here to see what it all means. So I started with that function, and then I implemented some of the ideas we were discussing before the break, and specifically that antibody-dependent enhancement. And I implemented it as was suggested earlier, having another term here. Actually, let me just make it a bit larger again. Again, if it's not big enough, let me know. Having an additional term here, so we have now, this is the basic term at which viruses infect uninfected cells at some rate B. And now I stuck in a second term where it's at B2, which is now proportional to the antibodies. So if there's B2 is 0, then there's no antibody-dependent enhancement. And as we increase this term B2 here, you will see we're kind of mimicking antibody enhancement. So I put this here, then I also have to put it there because the uninfected cells move basically from here into the infected group. And also I need to put it here because that basically means a virus and an uninfected cells disappear and turn into infected cells. So I need to put it in this equation. So that's what I did here. What that means is now I have a new parameter, B2, that I didn't have before. So I have to stick it up in here into my function call. And I set it such that default is 0. So by default, there's nothing, no antibody-dependent enhancement. And then we can play with it and tweak it. And then also I need to specify down here. This is basically that big vector of parameters that is being sent into the function that runs the underlying model. So I had to specify B2 here as well. And basically this notation B2 equals B2 just means there's a parameter called B2 and the value should be whatever is passed up to the function into the function up here, either the default of 0 or whatever the user gives to the function. There's just some R notation. So that's all I had to do for this one, for that part.
Could we briefly review what the research question is? I know we went over 5 different groups topics, so this one is.
Yeah, so for this one, the idea was, Paul discussed antibody-dependent enhancement earlier. And the biological idea is that if you have antibodies, it can actually make the outcome of an infection worse. And so we're the idea is, can we explore that with a model where we include antibody-dependent enhancement, and then we change the amount, the impact of this, and see what the result is on the infection. So here, this is antibody-dependent enhancement, because normally without it, the rate at which viruses infect cells is given by this term. And now we have this additional term. Basically now virus can infect cells more effectively or faster, and that is proportional to how much antibody there is. So if there's more antibody, then you get a faster rate of infection. And so the question is, as we tweak this B2 parameter, which is the amount of antibody-dependent enhancement or its strength, how does that impact the outcomes? And so the outcomes we need to talk about now. But is that part clear so far?
Yes, thank you.
Okay. So now we need to talk about the outcomes we want to track. So one suggestion earlier was we look at the peak of the virus. We already can do that because we get the time series for the virus, so we can just read of the peak like we've done earlier. So there's no need to change the code for that. Another idea that people often look at is we could track the total number of cells that are dying during the infection. That's sort of a, could be a measure of how bad the infection is. So for that, I had to extend the equation a bit because we're currently not tracking dead cells. So basically what happens is the infected cells will leave the infected compartment basically by dying, but we're not modeling the dead cells. At least we didn't in the basic model because they're not further participating. But here, now if you want to actually know the number of dead cells, then we need to track them. And that's quite common that you might build models that have compartments in them, equations that don't really participate in the process and they don't interact with others, but you keep them along for bookkeeping. And so this is basically what we're doing here. So we're tracking, this is also in some sense you track the total number of infected cells because all the infected cells will end up here as dead cells. So that's what I did here. I added another equation for D as in dead cells. And all they do is they just take those terms, basically the infected cells, and they arrive here and then they never leave anywhere. So in this case, the dead cells start at 0 and then all the infected cells reach the dead compartment. And then just the final number in the dead compartment is all the dead cells at the end. There's a question, are we not distinguishing between different subtypes and specific antibodies? No, we're not. So I think that might get too complex. And we'll see. If we have the time, we could play with that and try to include that. But right now, we're not. We're just looking at sort of one type of antibody. But you could assume that the antibodies you have there is to the previous one, that the A you start out with. So then I have the equation here. I then have to put it in here as well. And then I have to specify a starting value for the dead cells. I start at 0. I have to specify them here in the vector of initial conditions. And I think that's all the places where we had the dead cells. So those were the two changes I made to the model. I included another equation that tracks the dead cells, and I included this extra term, which came with its extra parameter, and that I had to specify. Also, you saw I renamed it. It's not a hard rule in R that the name of the file is the same as the name of the function. I personally like to do that, so I know that the function inside the script is just the same as the script. What really matters in the end is this name in here, but this way is nice, and they agree. So this is my updated function. And I think for the other question we were discussing about just the impact of changing antibodies on the outcome, we don't actually need to have any further details in the model. At least I didn't think of, but we can come back to that and discuss and potentially further play with the model extension. So that's my function. And then I started sketching out some scripts here. So the first one is the antibody-dependent enhancement. We don't need the DSAIRM package here anymore because we're now having our own function, which is this one, and that's the only thing we need. So instead of loading a package, what you need to do, you need to use the source command in R, which basically means execute this function. This function doesn't actually do anything, but sort of run it such that I can start calling it. So that's what this one does. It calls that simulate virus and IR new such that we can do it here. When you load a package, what happens is it basically does that in the background for all the functions that are part of the package. So you can access them all at once. Here, we're just doing it manually for one. So we load it, and then now I specified some vector for antibody-dependent enhancement. Again, that's the parameter B2 that goes from 0 to something higher. And, then we can explore it. What values do you choose for that? That's a little bit of exploring and fiddling, but you can already get an idea that, initially you want it very low. In fact, I started at 0. And then you want to slowly turn it up such that it starts becoming comparable and then maybe bigger than this term. So, if you know what your B is and maybe your A, that gives you maybe an idea what your B2 is. But likely you'll have to do some exploring, and that's what I had to do as well when I tried to set that. So right now what I'm doing, I make a vector. I include 0 here because I want to run it for not at all. And then I have a sequence, and I do this looks a little bit tricky, but basically what that gives me is a sequence that's linearly spaced in log space, because I might not know this value over many orders of magnitude. So now I'm going from 10 to the minus 14 to 10 to the minus 6, 50 values sort of equally spaced in log space. That's what this kind of notation does. So it just defines one vector. If you type it in, look at it, you see it's no values. It includes 0, and then it goes from 10 to the minus 14 to 10 to the minus 6. Then again, I'll define 2 vectors here that just contain the answers that I'm looking at. Here, the peak and the dead cells. I just fill them with zeros and make them the length of this vector here. So basically right now it's length 50 and has all zeros. And then when I run the simulation, I start putting in the values that I get. And then I ran the simulation. Initially, I just, without thinking much, put the default values in it, and nothing happened. And I was like, why does nothing happen? And then I realized that in the default, the antibodies are basically turned off. So if there are no antibodies, then of course nothing happens. So the default settings in this case aren't very helpful. You can try it for yourself. If you uncomment this and comment this out, you'll see that it doesn't give you anything good. So I changed it, and here, just for simplicity, I don't repeat all the default values. I just show the ones that I actually changed. All the other ones stayed at their default, like U and I and so on. So I set B to something and A to something. And basically turned on the B cells and the antibodies. And I also had to fiddle a bit with the infection rate, because with the basic setting, even for that setting, you already get a really big infection. And so there's not much enhancement being done anymore, because you already at the default get a really big infection. So I tuned that down so I can sort of by default, I don't get much. And then hopefully if I turn on that enhancement, things increase. Also for simplicity, I decided we're focusing on B cells, so let's ignore the T cells. Of course, you could really go into the equation and delete T and everywhere else. It's a bit tedious, and maybe you want it later after all. So an easier way in these models to turn on and off certain things is to just set all parameters that are related to it to 0. So that's what I did here. We start with 0 anyway. And so, if you see here in the model, there's GT and RT that leads to anything non-zero. So if I set GT and RT to 0, then the T cells start at 0 and never grow. So they'll stay at 0 for the whole duration. So basically I've turned them off. They're not in my way anymore. Now I can't do that here with the innate response, because in this model, the innate response actually induces the B cells, and the B cells produce the antibodies. So if I turned off the innate, I would also turn off the B cells and the antibodies in this model here. So I can't do that. I would have to change the model to take out the F term here and rewrite the model if I wanted to do that. So the innate response stays in this model here. And then here I run the model, and you've seen that now a few times before. We're looping here, and now I'm running for B2. This is my new parameter that determines antibody enhancement. I set different values for B2. And then for everyone, I pull out what I'm interested in. So I'm interested in the dead cells at the total number of dead cells. So basically that's at the end of the simulation, sort of at the very bottom of my matrix. I look at the number that's in D, and that's what I'm doing here. Basically pull out D, and then the tail just means the last one. And the peak is, again, I look at the virus load and I pull out the maximum, so that gives me the peak. And then I can plot it. I can just, we saw that earlier. Actually, I removed this. Saw it earlier. I now have a plot where I put this antibody dependent enhancement on the x-axis and both the peak and the dead cells on the y-axis. So that's what I've done so far. Okay, there's some questions. Let me answer them, and then we'll play around again. Is there any link you can click from the simulation result page online to the R code if you want to make any changes? No. So the graphical interface is just that. It's the graphical interface, and you can make changes with the inputs here, right? You can change the inputs, but you can't change the underlying model. So to do that, you need to go here, download the code, and then actually open the R code and change it like we just did here with this one. So that's, at that point, you have to basically then switch to that. I think that was the question. If that wasn't actually the question, then please reword.
Yeah, that's the question. I just wanted to know that you answered the question exactly. So this means that they have to be in the same folder, because I see this is online, and then the other one looks like it's in a folder. So that requirement of them to be in the same folder doesn't involve here, right?
Yes, so right now we just use DSA to get that function here, but now we're all independent. So now they're all sitting now in this folder here. I have them all in one folder, script 4, 5, and this one. I just copied this one here from the package, put it in the folder, made a copy, made a new one, and then I have these ones. They're now all just sitting in the same folder here. And that it's now completely independent of the DSAIRM package. At this point, you don't need that package anymore. At this point, it's just whatever code you're writing and doing.
Oh, thank you.
What does d_all NN stand for? So d_all is one of the vectors where we're storing the dead cells at the end. So I just call it all because, you know, it's all values for every one of them. And then this notation just says, you see, we're looping here over n. Earlier, I called it n. I renamed it here now to nn because there's actually parameter n of the model. I should probably still be okay to still call this n and they don't interfere, but it's always a bit iffy. So, you know, it's often good to not have the same, you know, if you see a variable here in the model with that, give it a different name. So it can be anything here. You also could call it counter if you wanted. It's just a variable that's initiated and that starts at 1 and then runs up to whatever the length of this is. So in this case, the length is 50 because that's what we specified here. So this counter just takes on values 1, 2, 3, 4 until 50. And then for every, I rename it to nn again. So every value of this thing for 50, what it does here, it takes that entry out of the vector. So the first, the second, the third, the fourth, which are these values that we have here in our, that we want to run for the parameter. And then at the end, once we've run the simulation, it sticks what we want to record in that slot of d_all. So in the first slot, the second, the third, and so forth. So at the end of running this loop here, which is this part here, we have for each value of the bvec parameter ran the simulation and recorded what we wanted and stuck it into a slot in this one here. If you forget that and just do something like this, then you will get either a complaint from R because you're trying to assign a single number into something that is actually a vector of 50. Or, you know, it might actually secretly do it, but always does the same. So you only has the same number at the end. So you need to, you know, make sure you just assign it into the right slot. So if at the end your plot looks weird, then that could be a reason for that. So there's a comment, turning off T-cell immunity ignores contribution T cells to antibody production. That's correct. In fact, we don't even have Th cells really in our model here. So as always, these models are approximations, and it depends on the purpose and the question if you decide that a certain approximation is okay or not. Since in this case, we're just pretending to solve an actual research problem, we don't really have to care. But if you really actually wanted to study antibody-dependent enhancement, then you had to think more carefully. Do I need to include this part, such as Th cell, into my model, or can I get away not including it? But yeah, you definitely always need to think about what you think is okay to include to get a model that still does sort of what you need it to do. Other question? There's a raised hand.
Yes, I have a theory question. We talked about this a little yesterday, but and we mentioned discrete time versus continuous time. But when you're actually working with these models, I don't know, how do you think about translating that to actual data that you would have collected? So because we have, I guess, model time, the scale at which we're modeling the phenomenon, but in real time, we may want to kind of make that connection, similar to how with population models, the time that we take to kind of reach the peak number of infected people is important. And so in our models, we actually have to know that even though these are continuous time models, a single time step or data was collected in days or weeks, but here it's on a sort of smaller scale with T cells and B cells. Is there an analog for us to think about time and maybe connect to data for either parameterizing the model or validating the model?
So I'm going to talk about something, but I'm not sure if what I'm going to say is answering your question. So if not, then please ask again. But for instance, if you look here in the fitting apps, where we now actually have data, and it doesn't matter much. So you see here we have virus load data. These are the greenish ones, and it's measured every day. And so then here we have our model, which is continuous in time. Virus load sort of is continuous in time. So then when you do your actual fitting, you just always extract the value of the virus load for that point where you have the data. And in this case, basically you look at the differences and you try to minimize the difference as much as possible. So while your model is continuous time, you can extract specific data points from your model and then compare them with the data for which you have the data. So in this case, it was measured every day. If it were measured every hour, we would extract it at every hour. Is that starting to answer your question, or?
Yes, it is.
Okay. Okay, so we can run it. You might have already done it. I hope you should be able to do it. As long as you put those scripts in the same folder, you should be able to just hit, in this case, the source button. It's a little bit, they have that run button, but the run button only does a single line. So the source runs the whole thing. So it should work. I take a second because, you're repeating it 50 times, running the model 50 times. And it's covering it. Let me zoom up. So here, that's the figure I'm getting here. I can actually increase it. So I have the vector at the bottom, the B2, starting at 0 and ramping up, and have these two things tracking the peak of the virus and the total number of dead cells. And it's a fairly odd pattern, I think. And I don't actually know why we see this pattern. So that's, this model is not, in some sense, not really that complicated, but in another way, there's already enough moving parts that one actually has to think about. And, I don't know right now. So we do see that, I've set up the model such that in the absence of that antibody-dependent enhancement, we actually don't really get an outbreak. So, it's low. That's why I adjusted B2 here. You could run it and see that for B2 of that value, you don't actually get anything. So you don't get anything. And then, once it gets larger, you get this kind of that idea of antibody-dependent enhancement. So you get an increase in the peak of the virus. And you also see here, sort of at the same time, you get down here, you have no dead cells because you don't get an infection. And then you see here the number of dead cells start increasing. And then the dead cells level off basically at the point where all the uninfected cells become infected and then die. That's probably somewhat biologically unrealistic, so we might have to tweak that a bit. But that's kind of maybe sort of behaving. Now this, why this goes up and then comes down again and has this kink and goes back up, I do not know. So, this would now require more playing around and exploration. And at that point, those kind of figures might not be good enough. And at that point, you might actually want to either through the graphical interface, which of course now we can't do really anymore because we hacked the model. But then, your own way, you might have to look at the time series and see what is the model actually doing in terms of, and you could do that here, right? We could here at every step, and actually let's do that here. It might be intuitive. Inside the loop, we can at every step plot part of the time series. Let's say we plot at least the virus. Maybe the infected cells. Now, what will likely happen is that it just sort of rushes by on the screen because it makes one plot, then the next, and the next, and the next. So that might not be too meaningful, but you see it sort of changing. Oh, interesting. There seems to be like a second later peak happening then somehow, and that's why we see this up and down then. So the red ones are the infected cells. Black is the virus, so we can look at it again. So initially they just sort of decline, and they decline, but then they come back up later. What might be happening is that, we're starting here with non-zero antibodies, that the antibodies decline, and then that leads to that spike up there. But I'm not 100% sure, so that one would need to sort of explore that. We could see what happens if we change the number of antibodies initially. See how things change. Kind of similar. So that wasn't it. There are some comments. Cody asked, is it steady state? No, there's not really any steady state here. We're just, running it out and reaching of the peak and the total. In fact, there can't be a steady state here because we're having an acute viral infection. So all we're getting is, virus, and then it goes down and it's gone again. To get a steady state here, we would have to turn on birth and death of uninfected cells. Without it, we can't actually get a steady state. And the question, why is time not changing? Well, we run every simulation exactly from time 0 to time 30 in those time steps. So that's why the time axis is always the same, but the outcome then apparently changes, as we just saw. We could try to get some more intuition by plotting the innate response and see what that one's doing. You can't even really see what this is doing. Yeah, I'm still not fully clear what's going on and why we're seeing what we're seeing. So, this is then try plotting antibodies. Okay, let's do that. some point. Not sure if I remember that correct. I want to not just do color, but also maybe change the type. Yeah, okay, no, it's dashed. So I guess the antibody is just kind of growing. Okay, then they're kinking here. See what the B cells are doing. Yeah, B cells and antibodies basically track each other because, you know, the B cells spit out antibody. So here now they're changing. When the B cells still go through the roof. Huh, it's interesting. So, you know, it's a somewhat not too complex model, not too complicated, does some weird, interesting stuff that I currently don't know if it is just some bug somewhere and we didn't specify it right, or some of the parameters are unreasonable, or it actually makes sense and something interesting is going on. And, you know, that's what you always have to do. Someone said the code doesn't run. Can other people get the code to run? Okay, Sean is nodding, so seems like at least one other person was able to. Just make sure all the 4 are in the same, they're in the same folder. That simulate virus and the R script. So then it should work. Oops, that's good. So that's okay, works for at least one person. So that's how far I got with this one. I got something to work, and it seems like we could explore the effect, and it seems like there's some kind of antibody dependent enhancement thing going on. And depending on how I change some of the other ones, you know, it might or might not have this weird kink, but at least that weird kink happened. And so whenever you see something strange, it's worth exploring. You know, either it's a bug, then you need to fix it, or it's actually something interesting, and then you can write a paper on it. So, but either way, you'll want to figure out what is going on there. And the good and the bad thing is that, you know, you have full control over everything with those models. So, you know, if you're an experimentalist, you can just say, well, that's just what the experiment gave me. That's the data, and I don't fully understand it, but I don't know what else to do about it. That's much harder to justify for a modeler because you have full control over everything and you can dig as deep as you want. So in the end, I feel like you can't get away with the idea of saying, well, I don't understand my model, but that's what it does. So that's just not, in my opinion, not acceptable. Then you just have to dig deeper until you understand your model and see what it actually does.
I had a question.
Mm-hmm,
Or
yeah.
can I ask in person? Yeah, I guess so. You had mentioned, so I'd asked earlier about like this. You're making the assumption that like we're ignoring differences between homotypic and heterotypic antibodies for ADE, right? I guess then this is sort of independent about the questions of like what the model behavior is, but I guess then this model is just kind of a very qualitatively different picture of ADE than I had envisioned from Professor Thomas's lecture. I don't know, maybe you can comment, but like I thought ADE was more about sort of these like intermediate affinity antibodies from a previous infection, which are causing this enhancement. And this model, like in this model, it's very possible for you to have ADE even in the absence of a prior infection, just because you're getting ADE from the antibodies that are being created by this like acute infection, right? And so I guess my question is, yeah, I guess, and then the question is, can an acute infection, does an acute infection lead to boosting of antibodies from a prior heterotypic infection, right? Because one could come up with an even simpler model, which was just like you have some level of antibodies from a previous heterotypic infection. If that's not even boosted, then you could have a simpler model of heterotypic ADE where you don't even have this dynamics, like these B cell and antibody dynamics. I don't know. Does that make sense? There's sort of is sort of yeah, I mean, Professor Thomas wants to jump in.
Well, let me try to answer, and then Paul can answer too. First, you're absolutely right. I mean, we're not really modeling what Paul has discussed earlier. This is a toy, right? We were just pretending we're doing research here, but we're not actually doing research, right? So we just pulled one of these models and did something that kind of looks like maybe ADE, but it's not exactly what Paul described. You're right. If we wanted to do that, we should have two groups of antibodies and some kind of cross-reactivity and features like that. So in that sense, yes, don't take it sort of too serious, this model. It's just sort of trying to show how that could potentially work if this were the question. The second one about boosting through heterotrophic immunity, yes, that can happen. You can have it that you have a flu is a good example. Paul mentioned original antigenic sin. So you have both the thing that your prior immunity might reduce boosting of other ones, but it can at the same time there can be some boosting going on. If you get a somewhat related infection, but it's not exactly that. If the B cells are close enough for the T cell, they might get some bystander stimulation, is what people sometimes call it. So that can definitely happen.
Right, yeah, certainly in the case of influenza. I guess then my question is specifically in the case of dengue for this ADE, is there boosting of heterotypic antibody? Like, this is an empirical question. Is it known whether in dengue this happens?
Is the question like, it's called back boosting, where you get the new infection and then the old infection B cells expand. Yeah, that's definitely empirically shown, not just in dengue, but in flu and in SARS-CoV-2. You actually back boost to the common cold coronaviruses. And so the cause of that is that you've got all these memory B cells, just numerically, they're huge. So even if they're relative to the naive response, and so even if their affinity or avidity is much, much lower, there's still reasonable likelihood that they get pulled in to the germinal center and activated, even if they then end up don't doing anything.
Thank you so much. That was very helpful.
Okay, yeah, I do want to emphasize, right? Don't take it too serious, right? We don't have the time to do a full-blown research question, but hopefully you get the flavor of it, how you would do it. But if that was your actual question, you should really carefully think about, okay, what do I need in my model? What can I get away with? That said, if you look, for instance, at the within-host dengue models that I posted the link earlier and Cody put it in the Slack, you will see that they're actually fairly simple. They're just a few equations. So, if you pick it right and do it right and use it to answer the right questions, you can actually justify ignoring a good bit of detail that in some sense we know happens, but maybe it's okay for your specific questions to ignore it. There was a question in the Slack about these lines and that it doesn't show. So one thing is you need to make sure it's inside the loop. So here the curly brackets that show your loop, and so it needs to be in there. And also I did another thing that maybe didn't quite notice. There was a statement here, this graphics off at the bottom, and I moved it at the top. I don't know if that will do much, but it will basically shut down the graphic, this plot, and then sort of build it new. But if you shove that here and then put those lines in here, it should work. You should be able to see them as it runs.
I will move the graphics off to the top then and check, because I have it at the bottom right now.
Yeah, see if that makes a difference. What it should, if it's not there, you just keep plotting it here and here and here and here, jumping back and forth between those two, which is probably not what you want. And any other questions? Don't see any right there. There's a hand raised. Is that still from earlier, or is that a new?
I'm sorry, that was from earlier.
Okay. Well, we can come back to that, but I want to quickly hop to the other one where also I basically played with that. Very similar. I decided I'll use the same underlying model here. And now I just decided I'm going to vary the level of antibodies at the start. and see how the level of antibodies affects the peak of the virus. And then the discussion earlier we had was saying maybe that the duration of the infection, basically how long it takes until virus is gone. Here in this case, gone doesn't really happen because it just slowly goes to 0. So I just decided when it drops below 1 in the simulation, I call it done. So because I don't want this antibody dependent enhancement kind of thing in this model, I have, that B2 to 0, which is what I coded it here to be the default setting. So this part is turned off now in this example. But instead, I'm now having a loop again, and I vary now a loop over values in this vector here. You see, every time I basically supply a different value. You see now I gave it some things. I want 0 in there, that's no antibodies, and then I have them from 10 to the 2 to 10 to the 8. So a broad range of antibodies at the start of the infection. Again, I turned the T cells off here, and everything else I left at the default values. I pulled out the peak, so that's nothing new, that's like earlier. And then I also wanted to find the time at which the virus drops below 1. So this line of code here looks at when the virus drops below 1, and the which tells you sort of which row that happens. And of course, once it drops below 1, it keeps being below 1. So if you just type that which in there, you'll actually get a whole lot of numbers. But the first number in that is the first time it drops below 1. So that's what the min does. It gives me the minimum index at which it drops below 1. And then I just go back in and pull out the time value at that index, because then that's the time. So this gives me the duration. Let's see one new thing that happens. And then I do the same kind of plot here, just now the peak and the duration. And so basically now the scientific question we're trying here to answer, how does the peak of the virus and the duration of the infection change as the initial level of antibodies change, either because people had already from previous infections or they're vaccinated? How does that produce outcomes, different outcomes? Of course, all the other parameters are whatever the default values are, and that's might or might not be good values. So we can maybe play around with them a bit. So if I run this thing, this is kind of what I get. Let's try to understand it. So initially, it looks like the peak of the virus doesn't matter much because the antibodies seem to not be doing much. And then around here, as the antibodies increase, it's a steep drop to basically where there's so many antibodies there that you don't get a peak anymore. Basically, there's no more infection. So, basically that suggests maybe that, scanning over this regime is actually not that interesting. And, I should maybe start closer to there. So let's try that. Let's start at actually maybe 10 to the 5. Maybe go a little bit further and speed it up a bit. Fewer samples. Okay, see what's happening now. Okay, now we're seeing this a bit clearer here. There's level of antibodies where it doesn't really impact much. It goes down a little bit. And then there's some level of antibody where then there's just enough at the beginning to basically, stop the infection. And then there's no peak anymore at all. That's basically the starting values of the virus. So it never grows, it just declines. What it does for the duration is maybe somewhat interesting that, for some regime, the duration actually goes up. And then, of course, once there's enough antibody to not have an infection anymore, then there's no more infection, so the duration is 0. Why does it go up here? I'm not sure. That would, again, require exploring. And of course, we could do it the same way we did over here. We could copy those things over. And since it's the same underlying model, we can actually pretty much do the same. I'm going to move that graphic statement again to the top. All right, see what that how that looks. Okay, not much happening here. So it looks like what happened here, and we can run it again, is that the antibodies, as they increased, they kind of dampened the growth of the virus initially at the beginning, but then the antibodies decayed and the B cells didn't ramp up fast enough to produce new antibodies quick enough. And basically then you see that little dip in the virus, but then it still goes up and leads to an outbreak. And because you have this initial sort of dampening and then a slower ramp up, that gives the overall longer duration. So let's look at that again. So we'll watch the black one because the black is the virus. So that's the main one to watch. So you see normal, and you see it starts to sort of curve in, and here you see it's dampening, but which basically pushes it out. And then of course, at some point, there's nothing left anymore and you don't get an outbreak. So I think that we kind of sort of understand why we're seeing what we're seeing, and it kind of makes sense. If you have a lot of antibodies initially, then you get that effect. But if the antibodies can't clear right away and they're decaying too fast, or they're being sort of soaked up because they're binding to the virus and therefore they're being removed, but they're not binding enough virus to make it all go away, then the virus will still take over. And if the timing for the B cells to kick in, or the T cells, which we turned off here, isn't quick enough, then you might still see that big outbreak. I'm trying to think right now if there's, we know in general, if you have a ton of antibodies, you sort of stop the infection dead in its tracks. I'm trying to think one right now where, you might have an intermediate amount of antibodies that sort of keeps it at check, but then it just comes up later. Paul, can you think of any biological system where that actually might happen? I can't think of one right now. So, yeah.
I don't know if that pops to mind.
Yeah. So it might not be something that actually happens in biology. Also, of course, in a real system, once you're vaccinated, you not only have antibodies, you have memory B cells, and they will activate faster. We don't have this feature here in the model, right? We just have, we could, of course, put that in. We could actually do something. Why don't we just do this? We can say, well, not only do we have more antibodies, you also have more deep B cells. Now we should probably let that be much fewer B cells. We'll see. When we have the same length. So, so instead of having the B cells all fixed now, they're not changing too. So, basically we're starting with no antibodies, no B cells, and then antibodies grow from, 5 to 9, 10 to the 5 to 10 to the 9, and B cells from 10 to the 1 to 10 to the 3. So now assuming each one represents a, better vaccinated person that both have more B cells and both have more antibodies. So everything else should remain the same. So let's see what happens when we run this. It looks, let's see what the outcome is there. Still, it's not as sharp anymore. So it seems like at this point, the B cells came in somewhat fast enough to prevent it, but not quite fast enough. We could now, of course, tweak and change some of the parameters, such as, let's see which one is the parameter that controls the speed of the T cells, like, for instance, GB. We could increase GB. It's a default of 1. Let's see what happens if we set it to 2. It might be way too fast, I don't know. But basically that now just means the B cells are ramping up faster, which means they should come in earlier, which I would expect to dampen this and reduce it. Let's see what happens. Now, of course, it might do other stuff too. We'll see. Yeah, it looked like there was much less of an effect because the virus was always shut down quickly. You see, there's much less of this effect here. So it does what we think it should do. Okay, where should we take them? What should we do next? We have some more time. We can play around with it, or we can look at some bits of code or anything that's unclear. So whatever you want to do.
Can I ask a question? It's a bit basic one, or maybe a step backwards. So will you explain the code? Like what did you write? What it stands for? So you're not so good at R, like simulate, or like there was another one, BVAC. So especially BVAC code, I couldn't understand.
This one here?
Yeah. And 1 and 3 and length, what does it stand for?
1 and 3. This one?
In BVAC, like sequence.
Oh, okay. So that is an R command that just says make a sequence of numbers that start at this number, go to this number, and have this total length. So if I just copy it into the R console, see it starts at number 1, goes to number 3, and has equally spaced 30 numbers in between. So, if I do 10, it just gives me 10 equally spaced numbers. If I say go to 5, it gives me 5 equally spaced numbers. So that's just an R command to quickly get a sequence of numbers. And then what I'm doing here is because, some parameters like, in this case, or initial conditions might have a big, range over which it's realistic, right? Often in immunology or biology in general, we think in terms of log scale units, right? So it's not like, just 2 or 3 times as much. It might be 10 or 100 or 1,000 times more. So to sort of span a nice range, I want to span the range not just in linear. So instead of just going from 1 to 3, I'm telling it to go from 10 to the 1 to 10 to the 3. So you see, that's why I do this 10 to the sequence. So I get numbers that now go from 10 to 1,000, and they're equally spaced now in log space. So if you see here, when I plot it on a log scale, they look kind of equally distributed. If I didn't try to do that, if I just said, make me numbers from, if I told it sequence 10 to the 3, 10 to the, or 10 to the 1, 10 to the 3, length equal 30. You see, it does that equally distributed now, but in linear space, which means, they're bunching up much more up here at the high numbers. And all of these are 700 or more. And, the low numbers, there are much fewer of them. And that gets more extreme if it gets bigger. So if you want to sort of equally spaced in log space, this is sort of a way you can do that. But so basically that's what it does. So BVAC just produces this thing here. Those are the numbers that I'm pulling out of here in this loop. So then I pull, each time I run it, I pull another one of these values out here, which is now my starting value for B. And I pull another value for A out, which is my starting value for the antibodies.
And then BVAC, like down there, row 27, does it put BVAC in a list if you put NN like numeric? That's what it does? It puts in a list form something?
No, it pulls it out. So, if I have BVAC 1 gives me the first one, BVAC 10 gives me the 10th entry. And since NN is a thing that goes from 1 to 30, every time it comes by, it has another value. So first time it's 1, so it pulls the first one out. Next time it comes by, it's 2, so it pulls the second one out. Then and so on. So each time it pulls just one number out of this vector. So if you see single square in R, that means index pulling out. If you see double brackets, that usually has to do with lists in R. So that's just, every programming language has their own way of sort of indexing and pulling things out of bigger things. And, that's just something, depending on the language, one needs to learn, and R does it that way. If you programmed in another language, like MATLAB would, for instance, do it like this with curve brackets. So when I switched from MATLAB to R, I don't know how often I made this mistake. So, but there's just ways that you pull out individual elements. And here you see another trick, with the $. That's another one where I pull out an element. So res, it's this list thing, and then R has this convention that elements of that list you can pull out with a $. So you see that one. So it's just every language does it differently, and so requires a little bit to get the hang for a certain language, but once you know how to pull it out, that you can use. And often there's more than one way. That's one thing that's both really nice and really annoying about R, is that there's always at least maybe 10 different ways of doing something. So you might see it and learn it one way, and then someone else does it another way, and you're like, what are they doing over there? But they might be doing the same thing, they're just pulling it out differently. So I could, for instance, do I can pull the uninfected cells out like that, but I could also do it like that. Sorry, curly brackets. Gives me the same thing. It's just two different ways of grabbing into that. In this case, TS is the data frame. And this means give me the column U, all the values. And this notation does the same thing. So. Other questions or suggestions of what we should try out with this code? Or if we should change our model or try and answer another question. No ideas?
I have a question. Is it possible that here also we can have sort of any distribution that the compartments follow?
No. So your compartment is just a thing where you just count total numbers in that compartment. So if you want to have heterogeneity, then what you would have to do in these kind of models is you need to sort of stratify. And that doesn't give you a distribution, that just gives you sort of a types. And we can actually, try to do that now, and try to actually do the dependent enhancement model with two types of antibodies. But you can't get it a distribution. So if you want to get it a distribution, then you actually need to change your model. You need to either do it with a PDE where you have some other characteristic that you track, or you go to sort of an individual based model where you can give every person or every cell their own characteristics, and those characteristics are drawn from a distribution. So in these models are basically sort of describing the average behavior. If you think that the spread is important in these variables, you need to change it. Now we saw how you can basically draw parameters from distributions and run the model. That's possible. But for the variables, the quantities you track, like the virus and the T cells and so on, you can't do that easily with those kind of models.
Okay, thank you. And for the parameters, how will you change the values that you wrote for the distributions?
So you would do that approach that we looked at earlier today, the uncertainty and sensitivity analysis. Instead of fixed value, you would now sample the parameter from a distribution. And of course, you have to then run your model for every sample. And then you will get, based on the distribution of parameters, you will get a distribution of outcomes. So that's how you would do it for the parameters. And you can do initial values too for your variables. So you can, the starting values, like in this case here, Bmin, Bmax are the starting values for the bacteria. They can come from a distribution too. But then once you pick that and you run your model, then there's no real notion of distribution anymore for the variables.
Okay, thank you.
What about changing things after some time has elapsed? I'm not sure what that means. Could look at some scatter plots. We could, but we've done that before because I gave you code before where we looped over two different things. So, you would do that here again. You would now just have another loop here for something else, and then you would have one loop inside of the other loop, and then you would just change them at the same time. And so people are interested, we could do that, but it's conceptually not maybe that different. So I was thinking the other thing we could do, we could hack this model to try to include that antibody dependent enhancement bit. Opinions?
I like that idea.
Hmm?
I like that idea. The hacking model idea.
Okay, let's do that. I think that might be more informative because that, that's what you would need to do, tweak a model, change it. So let's first think what we actually need if we want to do that. So we now say we have, in previous infection, a certain level of antibodies, and now a new infection comes along. And there needs to be some distance between the previous and the new. I'm not fully sure yet right now what exactly we're trying to do, but let's just change the code a little bit. So I'm just now gonna include a second type of B cell and a second type of antibody. And I'm just for now assuming they're independent. So they have all their, I'm just putting 2 behind everything, behind the parameters that control them. So growth rate, B2. So that's basically, it would be now the new equations for this. We still assume they're induced by the innate response in the same way for now. So that's what we would have here. Then of course we would need them down here as well. 2 extra equations, B2 and A2. We now have a whole bunch of new parameters here. So let's see, we have RA2, DA2, KA2. I guess everything that has either B or A in it will be a new parameter. GB2, RA2, DA2. Let's see, are we missing any? GB2, RA2, DA2, KA2. Capital, yeah. Okay, so these are the new parameters we would have here. 2 new equations. We need here. One thing to note is that the order often matters here. Not always, but it's always good to sort of have these equations and especially those things in the equation in the same order as you start your initial conditions, because that package you're using here, the DESOLVE package, can be picky about that kind of thing. So you want to make sure you do that. And so now we need to stick them in here too. So put them all here at the end. Actually, we put them in here, I think. Right before B2, yeah. Often if you give them names, it doesn't matter quite so much, but it's just safer to make sure both the slot and the name is the same. Okay. Okay, now we have the next 2 B cells, but they're not doing anything right now. So now we need to let them do something. So I guess everywhere up here, we should, well, how do we do antibody dependent enhancement now with this new setup? How would we model that? I'm not sure.
Would it be just on the make the last term in the U equation A2 rather than A, something like that? So it's the old I'm assuming A2 is like the old antibodies.
So yeah, let's assume these are the previous B cells, and these are the previous antibodies. So they're starting at some level. Then we have to decide if we even want them to have the same kinetics as the current one. You know, the B cells to the previous one should be induced at that, but we can always set GB2 to 0. That would mean that basically the old B cells are not triggered by the new infection, if we think so, or to a much lower value. So we can decide that. So now we would basically say that the previous B cells or previous antibodies are leading to that enhancement part. So it would basically here be B2 is already okay, A2. A2, and here, A2. I think that's what we need. So let's see if we can translate our model into biology to see if it does what it does. So now we have equations for previous B cells and antibodies, B2 and A2. We'll start them at some value. We can let the B cells expand and the B cells make more antibodies if we want to. If not, we can choose this one to be 0. If this is 0, then there's also no production. And this one could, this one here. We would need that up there too. We would basically need to let them here be. We assume these, well, we can decide, but basically this means both the previous antibodies and the new antibodies also do their job, which means they're clearing virus. So we're assuming these ones do both. But we could say, well, these old antibodies are actually not doing that at all. They're useless in clearing virus. So we could set Ka2 to 0. Then the only thing they would do is be bad, which means they would lead to more infection by virus in this process. Or we could say they can do both. They can both be bad, which means a non-zero B2, and they can also be a little bit good by helping clearing virus if that Ka2 is non-zero. So we have that, and then the current antibodies and B cells just do their thing. The current antibodies now have nothing to do with antibody enhancement anymore because they're not in this equation anymore. It's just the old ones. So basically, the new antibodies to the B cells and antibodies to the current one do their thing, and the old ones do something maybe helpful, maybe not helpful. So I think we have the parts we need in here. Oh, I'm realizing here we need two starting values for that. So any thoughts on if I'm missing something? Okay, Cody says run with 0 antibodies, run for several days, take the final exit, then add. Yeah, but that's actually more complicated than necessary. We could do that, but we could just start this model with some level of antibodies here that we think happened, however it happened. So, you know, if we thought that was a real model, we could run it and then take the predictions from that model as the start for the new. But we might not even know what we get from the original, so we can just explore it for this. So first check is always, are there any mistakes in the code? So I'll hit the source button. That actually doesn't tell you much yet because it just makes the function available, but it doesn't check if it's okay. So it could still quite plausibly not work. So now I'm just gonna call it real quick with its default settings. Okay, I renamed it here. So I want to rename it here too. Let's try again. Okay, it ran without error. So that's a good first step. That, you know, most of the time that doesn't happen. Most of the time you get some kind of error message because you forgot a comma or something else somewhere. That doesn't mean it's right. It just means there were no obvious coding errors. So now we need to explore, you know, if it's right. So I'm going to keep this script. Just make a new one. That's just a new script now running the new one. So we still have the same kind of setup. We have the B2, which is the antibody dependent. We can still say we look at the same stuff here. We run the simulation. Now we need to think about what are we doing here. So we start with some values for B and A. These are our new ones. So they've started some non-zero value, but are not that large. And then we have our old ones, which we could vary or we could keep fixed. We have now two ways we can sort of explore antibody-dependent enhancement here by saying there are different levels of antibodies in there. So we could vary A, or what we're doing right now here, we're just varying B2 in this one here. But just gonna see if we can plot those two. I think everything else should maybe work. We'll see, fingers crossed. Let's run it and see what happens. So something happened, something ran. Here we're getting the fact that as we increase it, the peak goes up. So that's consistent with antibody-dependent enhancement, and more dead cells, that's also consistent. So I think we probably have something now that's closer to the biological question, where we now have the two, the old and the new, and we're running it now. We'll likely have to do some tweaks here. So suggestion in the chat, do we want to turn off production of the old B cells? We can do that. What did we call them again? That would be GB2. So that would basically now mean biologically that that those B cells, the old B cells, are so mismatched that they're not induced at all, not even some bystander induction. So that's sort of an extreme, but it's often actually very good to explore your model at the extremes. So that's sort of a general suggestion, especially if you build your model, turn on things to their extreme, which means 0 or close to infinity, really high, for things where you know what should happen or are pretty sure, and then make sure that does happen. Because especially once you start building bigger models, understanding all the moving parts at the same time is really hard and close to impossible. So you basically want to try subparts of your model. Like in this case, turn off the T cells, just explore the B cells, and turn off the B cells, just explore the T cells. And then once you are okay with the behavior of either one of those, then you can turn them on both at the same time. But if you try everything at once, it's usually very hard to understand what's going on. So let's see how this will change answers. So you see the B cells here, the old ones are flat, so that's good. Looks sort of qualitatively similar. Again, as it increases, at some point the peak goes up. So for that level here, basically it means without the enhancement, you don't even get an infection. Now, there might be that's not what you want. You want to be in a regime where you get an infection all the time. So then you can tweak some of the other parameters. So in this case, I think you would be tweaking, if you have the base rate of infection to be higher, then you would see a change there. I think now you get an infection even for no antibody-dependent enhancement. Yeah, you see that here, you got virus now, even at the start. So yeah, you see you get some virus here. It's not at 0, it's at some value. But then you get the enhancement again here. It goes up as your BP goes up. Okay, so we built two model versions. One that was sort of a simple alteration in this one that now has, how many? We have 3 more equations in the model, 3 more things we track, new type of B cells and some dead cells. And then of course we have a bunch of new parameters, and we have a new process here, this ADE type process. Any questions on what I just did here? Or thoughts, comments before we wrap up that session? No, well, if there are none, then I think this might be a good point to stop this session here. I know, especially if you've never coded before, this is a lot to digest in just a short time. But I'll give you all the scripts so you can play with them, and I will add some comments a bit more so you understand what each line is doing. And then often, you can just, if you're completely new to coding, just sort of take a line, stick it into R, and see what it gives you. The outcome, and this way explore. But I hope the general process is now sort of clear how you can do it. You have some kind of scientific question, and if you're lucky, there is already a model such as one out of the DSAIRM package that you can use and modify. If that's not the case, then you would just basically have to write all this code here yourself. You see, it's actually not that much code. It might look intimidating, but it's 60 lines of code and a good bit of comments. So it's actually not that much code once you get the hang of it. So then you would basically write it. You make sure that you have the pieces in the model that you want to explore and that you think are important. The pieces that you think are maybe not that important, you leave out, you ignore. Here, for instance, of course, we have only one equation for the innate response. We know now, based on what you learned from Paul, that there's close to infinite number of different components of the immune response, of the innate response, that all do kinds of different things. So if for some reason you decided you need them in your model, you could extend that. You have an equation for IL-2 and IL-10 and IL-8 and IL-6 and whichever one you want to track. You could do that. But of course, then you would need to make equations for them. You need to make parameters for them. You need to get values for these parameters from the literature. So it all gets more complex and might not be worth it, depending on the question you have. Of course, if your question is what would happen in the system if I depleted IL-2, of course, you need to put IL-2 in your model. But if you're not interested in that, then you try to just do the minimum that you need to answer the question you're interested in. And then after that, once you basically specified your scientific question, that's really the hardest one, and figured out how you want to address it with the model. And then the rest might be tedious at times if you have to write a big model, but not really hard, right? You just write your model, you debug it until that thing works, which can take time. It can be frustrating, but again, it's not, I wouldn't say really hard. It's more, can be tedious. And then you run it, you explore it initially, you make sure everything works, and then you decide, okay, these are the figures I want to need for my papers, and then you run it for real and make nice figures, not these ones we've made here. You don't want to publish that, you want to make good looking ones, but again, that is not that hard then. Okay.
Can I ask a quick question?
Sure.
It's about differential equations. Is there a resource you would recommend somewhere, or some guidance tool with differential equations? So I think my biggest challenge would be with that. I would come up with my question, but how to mathematically express that.
Yeah, it's a bit tricky because when you classically learn differential equations, the focus is really on doing simple ones enough that you can solve with pencil and paper. That's almost every differential equation book you pick up would do that, which most of the time is not useful for these purposes here, because you will just implement it on the computer anyway, so you won't actually do any differential equation math, so to speak. So really the one skill you would need to learn here is how to translate your question into a set of equations, and then at that point you just stick it in the computer and run it. For those kind of resources, I think the best ones might be these kind of mathematical biology textbooks. No, there isn't one completely on the within host level, but the population level, like the SIR models, are somewhat similar. And then I think it's mostly just, a lot of practice and reading papers like this and trying to really understand, okay, how are they mapping a certain processes to models? I think if you work through all the models in the DSAIRM package and really try to understand how that description of the processes maps to the model and back, you'll actually get pretty far in sort of understanding these models in the way you need to understand. And for most purposes, you don't need to know any, differential equation related math, what you would learn in a classical math course on differential equations. That's for most practicing, people that want to solve practical problems that they don't want to publish in math journals. You don't need that kind of stuff.
Okay, thank you.